In the last chapter, we talked about Gibbs free energy, and Gibbs free energy and equilibrium constants are certainly related to each other. So if you have a delta G and you want to find K, or you have a K and you want to find delta G, you can use this expression, delta G equals minus RT natural log of K. R here is the so-called energy R. It's the 8.3145 joules per mole Kelvin, and you want to make sure that you use that. Temperature, of course, will be Kelvin, and this works for all the equilibrium constants you can think of. This is just a sculpture called Equilibrium, supposedly. I don't know. I thought it was kind of cool and artistic, but it really doesn't have anything to do with it. But anyway, if you are at standard states, if you're using that little superscript degree symbol, delta G 0 superscript equals minus RT natural log of K. However, if you aren't at standard states, then you can use delta G, the delta G at non-standard states, equals delta G at standard states plus RT natural log of Q. So if you have some kind of weird set of conditions, Q will help you go from one to the other. Honestly, the one we're going to use the most is delta G equals minus RT natural log of K. And any of the equilibrium constants we're going to talk about, and there will be quite a few, you can turn that back into a delta G using this expression, which is a pretty cool thing. So let's say you wanted to find the equilibrium constant K for this reaction, dinitrogen tetroxide going to nitrogen dioxide, knowing that the delta G, the Gibbs free energy value under standard conditions, is a positive 4.80 kilojoules. All right, no problem. So what we'll do is you'll use minus RT natural log of K equals delta G. But there are a couple of things I want to tune you into. First of all, notice that the value of R is joules per mole Kelvin. Mole isn't showing, but that's what's there. And the delta G values, like delta H, are usually in kilojoules. So one thing you want to make sure you do is you turn your kilojoules into joules first. So that way you're using a delta G with joules and an R value in joules. You can also convert both of them to kilojoules. It doesn't really matter, but you don't want to mix joules and kilojoules together. So anyway, delta G positive 4,800 joules equals 8.3145 times the Kelvin temperature, 298 Kelvin, times the natural log of K. So we'll solve here for natural log of K. That equals minus 1.94. If you anti-log it, which means take e to the x to it, so e to the minus 1.94, the equilibrium constant here is calculated to be 0.14. And at first it might be hard to make sense if these values are sensical or not. However, remember that delta G values greater than 0 are the ones that are non-spontaneous, and non-spontaneous is just another word for reactant favored. And in this chapter, we've seen that K values less than 1 are reactant favored. So if you have a positive delta G, you should have a K that's less than 1. Likewise, if you have a delta G which is spontaneous, i.e. it's less than 0, it's a negative number, then that means you should have a product favored K, a K that's greater than 1. So delta G's that are positive go with K's that are less than 1. Delta G's which are negative goes with K's that are greater than 1. And that does sometimes help to figure out if your answers make sense or not. So here we have a question. At 452.2 Kelvin, an equilibrium constant's found to be 0.444. Let's calculate delta G. Okay, so delta G equals minus RT natural log of K. So minus R, 8.3145, times T, the Kelvin temperature, 452.2, times the natural log of 0.444. And that's going to give us a delta G number. Now, the delta G number we initially have will be in joules per mole. And we need to convert that into kilojoules per mole. So we'll divide that number by 1,000 to get the actual desired kilojoules, which makes sense for our answers. So if you do all that, that comes out to be positive 3.05 kilojoules per mole. And again, to make sense of this, remember that K's less than 1, i.e. 0.444, those mean reactant favored. And reactant favored corresponds to a non-spontaneous delta G, a positive number. So K's less than 1 and positive delta G's absolutely go together. Answer D wouldn't make sense. A negative delta G would be corresponding to a K value much greater than 1. one. And that's not what we have here. So anyway, these are just things to do. But watch the kilojoules to joules things on these. That's the only tricky part that I can think of. Otherwise, it's pretty good to go.